We are going to present the topic on short channel effects in 2D and negative capacitance FETs and their effects to reduce a short channel effect. We are the team members, myself VAIRAVAN and PRASANTH and KABILESH. In this presentation, we are going to see what is short channel effect, what short channel effect in 2D and why they are important in 2D, and the negative capacitor and some of the effects that to reduce the short channel effects. First, we're going to know what is short channel effect. Short channel is a set of phenomena occurring MOSFET, that is metal oxide semiconductor device. Other similar electronic devices when their channel length is scaled down to few tenths of nanometers or less. These effects became increasingly pronounced as device dimensions shrinks or their expand significantly impact on our transistor performance. These effects are key challenges in modern semiconductor technologies as the industries grown in our natures to strive to create smaller, more powerful transistors. Short channel effects in 2D. Short channel effects in 2D are performance degradation of non-ideal behavior that occurs in modern electronic devices, particularly the transistor when their channel length is reduced. While coming to two-dimensional materials such as graphene, transition metals, and electronic properties are significantly different from their traditional three dimensions compared to the 2D. Now, the unique electronic structures in 2D leads to interesting novel short channel effects in made from these materials that produce. There are some of the disadvantages to reduce this effect. Come up with the upcoming slides to discuss. In two-dimensional structures such as graphene are more compared in 3D material, the unique properties are achieved. Why they are important in 2D? Short channel effects is significant important in 2D material due to unequal uh, electronic properties. Here are some short channel effects properties that can be used. Channel confinement. The nature means that channel length is increasing short. While the channel length is approaches nanoscale, short channel effect become more pronounced. High electric field. 2D material have a high carrier mobility and in short channel devices. And mobility degradation. In short channel 2D transistor carries experience more scattering events due to interaction with our substrate and their channel edges. Debit or the threshold voltage shift. Short channel effect like a drain induced barrier lowering can cause a threshold voltage to shift upon the region, leading suboptimal switching characteristics. Subthreshold slope roll-off is very important. The deviation from the ideal subthreshold in short channel devices affects the energy efficiency. In 2D transistor, where the energy efficiency often priority and minimize the SS roll off. Coming to the hot carry effect, which upon act on many of the regions or in higher electric versatility in 2D material can lead to hot carry effect where material is significant to the kinetic energy. Last and not least, scaling limitation. The pronounced short channel effect in 2D transistor can impose limitations these devices to be scaled on overriding this limitation, essential to pushing the boundaries and the nano electronics.
Negative capacitance field effect transistor. NCFETs are an innovative class of transistor that exploit negative capacitance behavior to achieve certain advantages in terms of energy efficiency and voltage scaling. The negative capacitance is a phenomenon where the capacitance of a specific moment decreases with increasing voltage across it. In NCFETs, a ferroelectric materials is integrated into gate stack. When a voltage is applied to the gate, the ferroelectric material experiences negative capacitance. Effectively boosting the voltage seen by the channel of the transistor is allow the NCFET to achieve the slopes. Then traditional transistor overcoming one of the fundamental limitation in transistor scaling. By utilizing negative capacitance, NCFETs can operate at low supply voltage while still maintaining the desired on current. This results in reducing power consumption and improved energy efficiency, making them a promising candidate for future low power electronic device. Next, working principle of NCFETs. Ferroelectric material integration. NCFETs incorporate a thin layer of ferroelectric material into gate dielectric stack of the conventional FET. Next, polarization and negative capacitance. Ferroelectric materials have a unique property called polarization. When an external electric field is applied, the dipole within the material align in a specific direction, resulting in a net electric polarization. Importantly, certain ferroelectric materials exhibit negative capacitance behavior. This means that as the voltage across the ferroelectric layer increases, its effective capacitance decreases. Next, operation at subthreshold region. NC are primarily utilized in the subthreshold region where the gate voltage is below the threshold voltage and the transistor is in the off state or the leakage region. Next, steepening of subthreshold slope. The negative capacitance effect enables the NC to achieve subthreshold slope values lower than the fundamental limit of approximately 60 millivolt per decade. In conventional FETs, this means that for a given increase in voltage, the NC FETs can exhibit a much larger drain current, making it more energy efficient and capable of finer transistor scaling. Next, benefit of NCFETs. First, lower power consumption. The most significant advantages of NCFETs is their potential to drastically reduce power consumption in electronic devices. By operating at low efficiency voltages, NCFETs can achieve similar performance to conventional FETs while consuming less power. Then enhanced energy efficiency. The step subthreshold slope achieved by NCFETs result in better energy efficiency. Device with NCFETs can switch more efficiently between on offset, reducing energy dissipation during transition. Then improved performance. NCFETs can offer high drive currents and faster switching speeds due to effective voltage boost provided by negative capacitance effect. Then voltage scaling. NCFETs enable voltage scaling, allowing electronic devices to operate at lower voltages without compromising performance. This is particularly beneficial for battery powered devices and energy efficient systems. Then transistor scaling. With NCFETs, it became possible to further scale down the size of transistor, paving way for more advanced and densely packed integrated circuits. Then compatibility with existing technology. NCFETs can integrated into existing semiconductor fabrication processor with relatively minor modification, making them a practical option for future semiconductor technologies.
Now we are going to see the impact of gate channel scaling effects. Before that, let's see what is meant by gate length scaling. Gate length scaling refers to the process of reducing the physical size of the transistor gate in integrated circuits as technology advances. The scaling has been fundamental driving force in the semiconductor industry, allowing for higher transistor density and increased performance and lower power consumption in electronic devices. However, as gate length scales down, it leads to several challenges, particularly in short channel devices. The short channel effects refers to the deviation of transistor behavior from the ideal behavior as the channel length is reduced. Let's explore the impact of gate length scaling on short channel effects. Drain induced barrier lowering. As the channel length is reduced, the electric field from the drain extends more into the channel, reducing the effective barrier height between the source and the drain. This phenomenon is known as DIBL and it results in increased subthreshold leakage current, causes devices to operate in an undesirable state even when they should be turned off. Drain induced gate leakage. Short channel transistors also suffer from increased gate leakage current due to the drain electric field affecting the gate channel junction. This is also known as DIGL and leads to the higher offstate current, which can significantly impact the overall power consumption of the device. Velocity saturation. As the channel length decreases, the carrier velocity can reach the maximum value called velocity saturation. This limitation affects the maximum achievable current in short channel devices and can lead to performance degradation in higher frequency applications. Gate induced drain leakage. In short channel devices, the electric field from the gate can affect the drain channel junction, leading to GIDL, which leads to additional leakage current and potential reliability concerns. At last, threshold voltage variation. Scaling down the gate length and can increase the sensitivity of the threshold voltage to random dopant fluctuations. This can lead to larger variations in the threshold voltage among individual transistors and the some chip, reducing overall device performance and yield. Let's see the impact of uh, subthreshold NCTMD PET. In the concept of short channel effects, the subthreshold NCTMD PET model refers to the type of transistor that addresses the challenges arising from short channel lengths in modern semiconductor devices. As transistors are scaled down to smaller channel lengths, they encounter the short channel effects that affect their performance. Let's see some of the effects. Induced barrier lowering. As the channel length decreases, the drain voltage starts to influence the channel's potential and leading to the reduction in the threshold voltage and increased leakage current. Subthreshold slope degradation. Charter channels experience reduced control over the drain current and resulting in a less steep subthreshold slope and higher off state leakage. Velocity saturation. Electrons near the drain region gain higher velocities, leading to velocity saturation and limiting the achievable drain current. Potential applications are memory devices, logic circuits, radio frequency devices, neuromorphic computing, energy efficient sensing. The subthreshold NCTMD PET model with the inclusion of negative capacitance effects aims to mitigate some of these short channel effects. By exploiting negative capacitance, the transistor can achieve steeper subthreshold slope, which can improve the transistor switching behavior and reduce leakage current, making it more energy efficient even at higher channel length. In summary, the subthreshold NCTMD PET model is a potential solution to counteract short channel effects in modern transistor, offering improved performance and energy efficiency in scaled down semiconductor devices.
Hello guys, thank you for your patience to listening this video. I hope this video is useful to you. If you like this video, support our channel by giving the thumbs up and thank you.